In this analysis, we will just focus on the major decking components. We won't be checking connections, such as the fastener shear or pull-out capacity. The analysis will also focus on the W3 or W3E detail with the steel crossbeam, timber nailer, and timber decking, which is the most commonly used configuration in all of our program countries. Crossbeams. First, I'll talk about crossbeams. Analyzing the crossbeams is the simplest. We can take our span conservatively as the 1.5 meter crossbeam length and the tributary width as the 1 meter crossbeam spacing. I've drawn this out here in red. And crossbeams take the full dead load and live load, picking up the entire walkway loading and transferring this to the cables. The nailers, in gold, just serve as bearing and connection plates between the steel crossbeam and timber decking. These will not be analyzed in depth because they are supported along their entire length and have sufficient strength and bearing to support the decking loads. The deck boards will only feel their self-weight. I've drawn these out in green, and in combination with the applied live loading. These are the trickiest components to analyze because it can either be simply supported or continuous spans. And additionally, different countries use different board details based on the availability of timber. In Eswatini, we use the W3E detail where there are 6 boards at 15 centimeter widths, and in Bolivia, we use the W3 detail where there are 5 boards at 20 centimeter widths. Now the diagram here summarizes the various loads and areas we might find along the walkway. The blue dotted line is our end condition, the simply supported beam of 90 centimeter length. In red, I've shown the point load that can be moved anywhere along the walkway. And in purple, I've shown the distributed line load along the walkway. In green, the 100 centimeter dimension is for the first portion of our continuous beam condition. Now regarding our various decking beam conditions, case 1 would be simply supported. This occurs at the beginning of the walkway, where we need to check our first 90 centimeter span deck beams for adequacy. Simply supported beams have the following equations, here in magenta, for point loads or the distributed loads. Case 2 is continuous. A continuous beam uses a different set of equations to calculate the maximum shear and moment, and deflects potentially as such, as I've drawn out in red. Load should be placed on a continuous beam as to maximize the shear or moment, and this isn't always intuitive for many spans, so we can use influence lines for more complex structures. I won't go into detail about influence lines here, but it is an important concept in structural engineering, and I'll drop an introduction video into the section below. So we can use the equations from the Civil Engineering Reference Manual to calculate maximum shear and moment for a fully loaded continuous beam, because in this case, this is what creates the maximum loading for 2 spans. And after getting our decking loads, our next step would be to check the adequate capacity of the materials using their section properties. The crossbeams are a C4 by 5.4 steel channel in Bolivia, or a C100 by 50 or a C4 by 7.25 equivalent steel channel in Eswatini. The properties of this section can be looked up in the AISC Steel Construction Manual. And do note that here I flipped the axes because in the steel manual it shows the C channel and its axes flipped 90 degrees. So I flipped it here. That's why X and Y are labeled counterintuitively. And then I've summarized the properties for the crossbeam and the deck boards here below for each detail. Then after finding the actual stress, we can compare this to the allowable stress as calculated by the NDS or AISC procedure. For steel crossbeams, we'll compare the load and capacity using the prescribed factor of safety. For timber decking, we will calculate a demand-capacity ratio, which is defined as the actual stress divided by the adjusted allowable stress. And we want that to be less than 1.